This video, we're going to be talking about how to calculate the total energy density for blackbody radiation. Particularly, we're going to be using Planck's distribution in order to get the Stefan-Boltzmann law, which tells me that this energy density is proportional to the temperature, and specifically that it goes as T to the power of 4. The way that we are going to do that is by integrating over all possible wavelengths the spectral density. Now, this spectral density is my Planck's distribution. Before we go into the problem, I'm going to give you this huge hint, which is the integral that I'm showing here is going to come up handy in order to solve this problem. I'm a great advocate for you to use computers to solve relatively complicated problems, but I think it's also very important to know, or at least be aware of some of values, constant values for integrals that have a very specific form, because in case you don't have access to a computer, then you can still, by knowing these values, get to solve a problem. Let's actually bring Mathematica and see what that is. So let's just start by calculating this same integral that I'm showing here is one that I coded in Mathematica. So let's just evaluate it. Yeah, sure enough, it's pi to the power of 4 divided by 15. Okay, so this is just for us to practice annotation and everything, but remember, in general, even if you don't have access to a computer, but if you remember the value of this very specific integral, then you're good to go, because you can now put your expression in terms of the shape of this integral in order to solve it. Okay, now the other clue about this problem is that right from the beginning, I already know that the answer is going to be proportional to the temperature to the 4th power. So I know that that's how my answer is going to look like. So let's start. The spectral density, it's going to be Planck's distribution function. Again, this integral is very important because now it gives me a clue of how I should manipulate my equation in order to get a solution that is relatively simple to this problem. So look at the denominator of this integral, e to the power of something minus 1, which is exactly what I have here, e to the power of something minus 1. So I have to do some manipulation, and the easiest thing to think about is that if this is e to the power of something, let's put all of this into something such that now they two resemble even more. That's what we call a change of variable. Now, that is a very important trick in physics and mathematics in order to get to a form that it's going to help you solve your problem more easily. Okay, so that's my change of variable. All this argument, let's just call it u, and I'm not calling it x just to prove another point, that this form of the integral is what it's going to give you this constant value. But x, in a way, is just a label. You can put any variable that you want, and as long as it complies with this form, the integral will have to be this one. Again, x is just a label, it doesn't have to be x. So let's call it u in terms of lambda, which is all this exponential, and now we can put lambda in terms of u. One thing that you should notice is that all these values, h, c, k, t, are constant. So what this is telling me is that the relationship between u and lambda is inversely proportional, with the proportionality constant being all these constants put together. Okay, so why is that useful? Because when I'm changing from lambda to u, I have to change everything related to lambda in my original integral. What are those elements? The limits, the differential of lambda, and everywhere with lambda itself appears in the equation. So let's work out the limits first. If it's inversely proportional to one another, when lambda is 0 in the lower limit, then u will have to go to infinity. And in the upper limit, when lambda goes to infinity, u will have to go to 0. Good. So now I solved the first problem, changing the limits appropriately. Now, with that, the next element I have to work out is the differential of lambda. For that, I can take the differential of u with respect to the differential of lambda. That's taking the derivative of u with respect to lambda. U, remember, it's all this value. So that one is going to give me the derivative of 1 over lambda. Since all of those are constants, I can take them out of the derivative. And the derivative with respect to lambda of 1 over lambda is minus 1 over lambda squared. Good. Now, what I should be doing is put this expression in terms of d lambda, so I can make a substitution, and that leads me to d lambda over lambda squared. It's equal to these constants times du. But here's something interesting. Look at how I arrange this d lambda, and this may seem a little bit strange at the beginning, but the more you practice, the more easily you can spot these kind of tricks. What I'm doing is factoring out d lambda to the power of 5 as lambda to the power of 3 lambda squared, and now look, I have d lambda over lambda squared, which is this term, which in turn is going to be equal to this much in terms of du, because I need to change the differential of lambda into the differential of u. And finally, this lambda cube, it's going to be done in terms of u. Okay, so let's do all the changes that we discussed. The limits now look from 0 to infinity, now it's infinity to 0. 1 over lambda cubed, which I have here. then times 1 over e to this, but this is equal to u, minus 1, and then the differential of lambda over lambda square is equal to all this term, which I'm writing here. Okay? Now, I have to group all the terms that I can together, cancel all the terms that I can't cancel, and then just put everything together. This hc is going to get canceled with this hc. This temperature is going to get multiplied by this t cubed, so it's going to give me t to the power of 4. Same thing for k and hc to the power of 3. So putting everything together, I have this bunch of constants times t to the power of 4. That's what my expression should look like. That tells me that whatever this integral is should be just constants because I already have t to the power of 4. So constant times another constant is still a constant times t to the power of 4. So what is the value of this constant? Look at this integral that I have here. They resemble a lot. Something to the power of 3 divided by e to the power of something minus 1 differential of that something, which is exactly the same thing, except for the fact that I have from 0 to infinity and here from infinity to 0. Well, how do we solve that problem? Okay, so let's suppose that I do that integral from from infinity to 0, and that gives me minus pi to the power of 4 divided by 15. Okay, but I told you at the beginning that the fact that I give you this integral is because maybe you don't have access to a computer. So another thing that is very important, and that's what I've been repeating, is making graphs is essential for you to get a good feeling of what's going on. So let's plot this function to justify why this is a constant value, but if I flip the limits of integration, it's minus that constant value. So let's plot the integrand, that function, from 0 to infinity, and sure enough, look at the shape that we get. So if we integrate from 0 to infinity, we get this much area, and if we integrate from infinity to 0, we get exactly the same area, but just in the opposite direction. The sign, let's say that it's just indicating the direction in which you're integrating. The total area will have to be equal to 0. So when you put these two together, sure enough, this should give you equal to 0. And that's it. So another way to write this one will be that the integral from 0 to infinity is equal to this constant value, which is going to be equal to minus the value when I flip the limits of integration. Okay, since I have the shape of this integrand, when I integrate from minus infinity to 0, it's still the same value, but now with a negative sign. So minus pi to the power of 4 divided by 15. Now, the only thing that I have left is just a bunch of constants times t to the power of 4, so I can signal all of, or group all these together into these one, let's actually call it alpha, constant times t to the power of 4. That's it. Now, probably if you look into your book or some other places, the Stefan-Boltzmann constant is going to be given for a very specific value. So what I want you to do is to show what is the relationship between the constants that I got here, alpha, with the Stefan-Boltzmann constant as it is written in some other places. Please let me know if you have any questions, and I'll talk to you later.